Hi, everyone. My name is Tim Roughgarden. I'm a professor at Columbia University. I wanted to spend 18 minutes telling you about my EC'21 paper, Transaction Fee Mechanism Design. If 18 minutes isn't enough, I encourage you to check out my YouTube channel, and in particular, the Israeli AGT seminar that I gave back in March. And if the EC Proceedings paper, if you'd like to read more than just what's in the Proceedings version, I encourage you to track down a 58-page report I wrote for a general audience, which covers all of the topics of this talk, as well as several other related topics. Let me begin by telling you just enough about blockchains to appreciate the mechanism design questions that I want to study. So fundamentally, a blockchain like Bitcoin or Ethereum, it maintains state. Okay, so state could be, for example, the current cryptocurrency balance of all of the users of the blockchain. In addition, blockchains execute transactions one by one, which change the state. For example, a fund transfer from one user to another would update both of those users' account balances. So for our purposes, that's really what a blockchain is. It's just a sort of serializing, it's a linear ordering of state-changing transactions. So why call it a blockchain? Well, transactions aren't published one by one. Rather, they're grouped into what are known as blocks. And blocks are published one by one. So first of all, blocks only come along every so often. In Bitcoin, you expect one block every 10 minutes or so. In Ethereum, you expect one block every 13 seconds or so. Secondly, blocks are not infinitely big. Okay? They have a maximum size. So for example, in Ethereum, transactions are measured by what's known as gas, which is a proxy for the computational requirements of executing them. And each block in Ethereum can only have at maximum 15 million gas. Think of that as translating to maybe 500 transactions or so. So Ethereum, you're seeing roughly 500 transactions published every 13 seconds. Now, for successful blockchains like Bitcoin and Ethereum, demand is way bigger than supply. So there's way more than 500 transactions per 13 seconds that would be highly interested in being executed on the Ethereum blockchain. So we have a scarce resource, okay, which is the real estate on a successful blockchain. And so we need a mechanism to figure out of all of the transactions that would be happy to be included, which ones are actually going to get included. That is a mechanism design problem. So how is this done right now? What's the status quo? Well, it's a very natural pay-as-bid mechanism. In this context, it's called a first price auction. So as a user, when you submit a transaction to the Ethereum or Bitcoin network, you're also responsible for attaching a bid to your transaction. So you make an offer of how much you're willing to pay in the native cryptocurrency to have your transaction executed. Okay, so to whom does that payment go? Well, it goes to the block publisher, whoever it is who publishes the block to the blockchain that includes your transaction in it. That is where your bid is going to be transferred to. So for example, in proof-of-work blockchains like Bitcoin and today's Ethereum, miners compete to solve a crypto puzzle. The first miner to solve the crypto puzzle earns the privilege of publishing the next block, and it collects the transaction fees that are offered by all of the transactions that it includes in its block. All right, so this is very natural. This was already there in Satoshi Nakamoto's Bitcoin white paper, and Ethereum and Bitcoin are pretty successful, so it clearly hasn't been a total disaster. But all of us are sort of very capable of criticizing first price auctions if we want. And in particular, we know that it's very difficult to figure out how to bid in first price auctions. But we've known that from a half century of game theory lab experiments. And of course, the problem doesn't go away just because you're on a blockchain. So let me make that a little bit more concrete, right? So if you're a user of Ethereum or Bitcoin, you're probably not actually specifying a bid yourself with your transaction. Probably it's going to be done on your behalf by software you use known as a wallet. So here I've shown you a screenshot of MetaMask, which is one of the most popular Ethereum wallets. And as you can see, it actually offers you a menu. It says, pay $22 if you want your transaction to be included really quickly. If you're willing to wait a half an hour, then you can just pay $17. And, smart people work in MetaMask, and they have algorithms that look at the recent bid data to suggest, what they think you should bid in the next auction. But first price auctions are hard. And anyone who's a regular user of Ethereum has had the extremely frustrating experience of following MetaMask or some other wallet's advice about the appropriate fee to set, and then having the transaction just hang for 30 minutes or more because the bid wound up being much lower than it should have been. So that really sort of throws the gauntlet to the mechanism designer. Like, can we have a better mechanism than a first price auction in some sense. For example, could we have a stronger incentive compatibility guarantee, maybe even something as strong as a DSIC, dominant strategy incentive compatibility guarantee, as we're accustomed to, for example, with a VCG mechanism? All right, so I hope you find the problem reasonably interesting and fundamental. How should you design a transaction fee mechanism for a major blockchain? This question is also actually super timely for the specific case of Ethereum, because literally just a few weeks from now, Ethereum's first price auction will be replaced by a much more sophisticated transaction fee mechanism, which is proposed in something called EIP 1559. EIP here stands for Ethereum Improvement Proposal. So, as I said, this is going to be implemented in just a couple of weeks. Back when I did this work in late 2020, it was not actually at all obvious that this proposal was going to be adopted and deployed. So this is a web search I did from a few months ago. As you can see, there's sort of hundreds of thousands of hits. In the news stories reference, there's some sort of controversy over whether it should be adopted or not. And because of that controversy, Tim Byko, this is again late last year, he's a major figure in the Ethereum community. He went out and sort of surveyed a bunch of the key stakeholders. For example, he talked to miners, he talked to people who write software wallets, he talked to exchanges, and he asked everybody, how do you feel about EIP 1559, and what could we do to make you feel more comfortable about making this major change to Ethereum's transaction fee mechanism? And several things were raised, but what I've highlighted here is one of the key impediments was, quote, the lack of a formal specification or proof for the mechanism that people can independently evaluate and critique, unquote. And let me emphasize, not a single respondent of the survey was like an ivory tower academic or a theoretician. These were all people deep in the Ethereum trenches, and there was a hunger for a formal analysis of this particular transaction fee mechanism. And so one of the goals of this work is to provide exactly that type of formal analysis. I mentioned a couple slides ago that blockchains pose some unique idiosyncrasies, and in particular make the VCG mechanism not easily implementable. So let me talk through what those are. Let me just first list challenge zero. This is something we're all used to. We're all used to the fact that participants in a mechanism can submit non-truthful information. So, for example, non-truthful bids. But we all know sort of how we articulate that we don't want this to have happen. We just say, okay, we want a DSIC mechanism, dominant strategy incentive compatible mechanism, where it's a dominant strategy for everybody to bid truthfully. All right, so let's get to the blockchain specific challenges. Okay, so first of all, as we discussed, blocks are produced by sort of the miner who wins a crypto puzzle, and whoever earns the privilege of producing the block has dictatorial control over the block's contents. You can put literally whatever transactions in that block that it wants. So you may have some allocation rule in mind for your transaction fee mechanism, but the miner has no obligation to actually carry it out, and in fact will not do so if it's not in its own best interest. So this leads us to the second incentive constraint, which I'll say formally on the next slide, MMIC, incentive compatible for myopic miners. Miners should be properly incentivized to carry out the allocation rule of your transaction fee mechanism. Another idiosyncrasy is that payments need to be defined purely by winning bids. Payments cannot depend on the losing bids. Why? Blockchains like Ethereum and Bitcoin, they're basically hermetically sealed environments. As far as the blockchain is concerned, if it's not on the blockchain, it doesn't exist. And so that means payments must be computable from on-chain information, and it's only the winning transactions that are recorded on-chain. The losing transactions are not recorded on-chain. So bids need to depend only on the winners. Challenge 3 sort of extends challenge 1. So a miner that produces a block, in addition to being able to deviating from your allocation rule however it wants, it can also act as a shill bidder. It's very cheap in this context to create fake transactions indistinguishable from real transactions. And so a miner, if it will boost their revenue to inject fake transactions, we should expect them to do it. Okay, we don't want them to do it. That will also be part of our MMIC incentive constraint. Final challenge, collusion. Specifically, collusion between the miner of a block and the users who submitted the transactions that get included in that block. Okay? So that's going to lead us to our second new type of incentive constraint. It's going to be called OCA proofness. I'll give you that definition in a couple slides. Okay, so this is motivated by the fact that in a blockchain setting, through smart contracts, it's actually really easy to form coalitions and sort of collude off-chain. All right, so just briefly, so we're going to have DSIC as an aspiration point. What are the other two guarantees that we'd really like to have? We'd like to be MMIC, incentive compatible for myopic miners. So that just means that a profit maximizing miner is motivated to implement the allocation rule of your transaction fee mechanism without injecting any fake transactions. Okay, first price auctions certainly have this property. In a first price auction, we're expecting a miner to maximize its revenue, pack its block as full as possible with the highest bids. A miner is generally happy to do that. The VCG mechanism is extremely easy to manipulate through the injection of fake transactions, and it fails MMIC, and that is the reason you never hear about second price auctions in blockchains, because of this vulnerability to fake transactions. All right, so that's the challenges 1 and 3, that miners can do what they want and inject fake transactions. We sort of want that to not be. We want a mechanism which is robust to those issues. We also want a mechanism which is robust to off-chain collusion by a miner and users. And so that brings us to the OCA proofness incentive constraint. OCA here stands for Offchain Agreement. So the formal definition is there should never be a way for the miner of a block and the users of transactions in that block to collude off-chain so that they're collectively strictly better off than they would be if they just did what they, did the obvious thing on-chain. Okay, so to make this definition as sort of hard to satisfy as possible, I'm allowing transferable utility, so arbitrary side payments between the miners and the users off-chain. So that's why it's about the joint surplus of the miner and the users. It should never be possible to have the joint surplus strictly higher off-chain than it would be if they just participated on-chain. First price auctions, for all their issues, they are OCA proof. Whatever side payments a miner and users implement off-chain, they may as well just do it on-chain through the first price auction mechanism. There's no reason not to do that. An interesting example of a transaction fee mechanism that fails to be OCA proof is if you try to use a reserve price. Okay, so if you try to exclude transactions that bid below a given amount, that bid below the reserve price, and you pay the miner for all of the payments of this block, then in fact, a miner and users can collude off-chain to completely evade the reserve price. It's as if the reserve price was zero. Okay? So reserve prices, at least naively implemented, don't work. They can be evaded by collusion. So those mechanisms are not OCA proof. Is there anything special about the blockchain setting that actually works in our advantage? Well, there is. Number one, this auction doesn't occur in isolation, right? Every 13 seconds in Ethereum, this auction is being run. And so in particular, for a given block, you could have the mechanism, for example, a reserve price, depend on the outcome of the previous blocks. And so you could adapt the mechanism over time depending on the outcomes of previous auctions. The status quo does not do that. The status quo is a first price auction every single block, ignoring the whole past, but you could make use of the past if you wanted. Benefit number two, there's tremendous control over what happens to the payments from the users of included transactions, right? Because basically what happens to those payments is literally in the protocol code. And there's nothing that anybody can do about it. So in particular, it's trivial in the blockchain setting to take users' payments and burn them, or to redirect them wherever you want, not necessarily to the miner of that block, to a foundation, to the miners of other blocks, whatever. So that's the second benefit. Okay, so you can really have hard-coded control over what happens to the payments of one of these auctions. All right, so the goal then, the technical question is, can we have a transaction fee mechanism that meets simultaneously these three incentive guarantees, DSIC, MMIC, and OCA proofness? First price auctions satisfy the latter two. Is there anything that satisfies all three? This is actually still an open question. I don't know the answer to that. Really nice open question. So I want to tell you about something that gets pretty close. And that's, in fact, the mechanism proposed in EIP 1559. I don't have time to tell you about it in detail. The mechanism does make use of a reserve price. Wait, didn't I just say reserve prices break OCA proofness? I did say that, but that's why in EIP 1559, the revenue from the reserve price is not passed on to the miner of the block, but rather it's burned. That's what allows you to save OCA proofness, by burning the revenue generated by the reserve price. How is the reserve price set? Well, here we take advantage of the past. So there's going to be a tâtonnement process which adjusts the base fee, the reserve price, so that it sort of is tracking the market clearing price. So if recent blocks have been really big, you're going to make the price higher. If recent blocks have been really small, you're going to reduce the price. Okay. Finally, there is a sort of emergency fallback first price auction as part of the mechanism. The hope would be that this would almost never be used. But in addition to paying the reserve price, users can, if they want, specify an additional amount on top of the reserve price that they're willing to pay. That would not be burned. That additional amount would be transferred to the miner of that block, like in today's first price auctions. So EIP 1559 was authored by Vitalik Buterin, who's also the founder of Ethereum. He actually went to EC just 3 years ago when it was in Ithaca, and he talks about how he had some nice conversations with members of the EC community. And he also, in that same blog post just after the conference, he said informally what his goal was behind the design, to sort of discourage strategizing by users, by miners, and to discourage collusion. So let's examine to what extent, so this is an informal statement, let's now formally understand to what extent the design achieves the stated goals. So I wouldn't give 1559 an A+ on the report card, but I would give it an A. Okay, so like first price auctions, it's always MMIC. Okay, miners are motivated to follow the allocation rule that's intended. Like first price auctions, it's always OCA proof. So there's never a way that off-chain collusion can improve a miner and users. And it's also, in some sense, usually DSIC, right? So one would expect it to be DSIC in 95 to 99% of the time. Now, we sort of see immediately it's not always going to be DSIC, because if you find yourself in a situation where the reserve price is 0, then it's literally exactly the same as the first price auction, which of course is not DSIC. But in some sense, this is the only issue. The only problem is if the reserve price is way lower than it should be. Why would that ever happen? Well, it's going to be because you just had a demand shock. So if you were just in a period of stable, low demand, and then all of a sudden the demand went way up, well, it's going to take some number of blocks for the reserve price to adjust accordingly from the old low market clearing price to the new high market clearing price. So there'll be a period of a minute, 2 minutes, something like that, where you'll lose DSIC. It'll really be acting more like a first price auction. But again, that should be really the uncommon case. Only in these transitory periods, switching from a low demand regime to a high demand regime. That's the only time that you actually lose the DSIC property. Otherwise, you have it. Otherwise, the mechanism acts like a posted price mechanism, where the posted price is just the reserve price set by the tâtonnement process. So I'm out of time. Let me wrap up with, let me just flash 3 open questions. As I said, it's open whether it's a transaction fee mechanism that meets all 3 incentive constraints. It would be great to study incentive issues at a timescale longer than a single block. So, for example, persistent collusion by miners over multiple blocks. There's a great game theory question there. And then we also need theory about what's the best way to implement the tâtonnement process. So that's it for me. Thanks very much.